Covariant versus contravariant tensors. The choice between using covariant or contravariant tensor forms, or a mix of both, depends on the context of what you're trying to express mathematically. Tensors are geometric objects that transform in different ways under coordinate transformations, and the distinction between covariant and contravariant components reflect different transformation properties. So let's break down the key reasons for using each type and why you might choose one over the other in specific formats. Let's start with contravariant tensors with upper indices. These objects represent objects that transform in the same way as coordinate basis vectors. One comes to learn that contravariant tensors typically represent things like velocities or displacement. For example, let the vector v be given by the contravariant vector here, upper mu. Then the transformation rule here applies, recalling this notation from our last video. So the key property of contravariant vectors is that they describe quantities that are associated with a position or a direction in space. So contravariant vectors are used for things like velocity and displacement. This part being the basis vector and this part being the contravariant components. So when is it appropriate to use contravariant tensors? Again, the thought here is anything that deals with displacements, or velocities, or momentums. They point in some direction with some magnitude. A velocity vector changes its components as the reference frame changes, but even still it remains a vector in the transformed coordinate frame. Direction-based quantities are represented by contravariant tensors. You use contravariant vectors because they naturally follow how directions transform with a change of coordinates. Contravariant components are typically ones that describe how a point or a vector changes its position with respect to a new reference frame. Covariant tensors with lower indices. They represent objects that transform in the opposite direction to the coordinate basis vectors. Essentially, covariant components describe how a quantity interacts with the coordinate system itself, rather than the underlying geometry. So what are covariant tensors useful for? Well, for example, let's take a look at what a covariant tensor looks like again. So the components of the vector, we'll call the vector W here, with lower index mu. Transforms according to the rule, again using the notation that we had developed in earlier videos. Covariant vectors, or one-forms, are often used to represent things like gradients, or differential forms, differentials of scalar fields. And this is because they naturally describe how quantities change in relation to the coordinates. So when should we use a covariant tensor? Again, covariant tensors are things like gradients, differential forms, and dual vectors or covectors. Covariant vectors and tensors are typical when you are working with, say, the gradient of a scalar field, or a one-form. And what this means is that the gradient of a scalar field function is a covariant vector because it describes or measures how the scalar function changes in the coordinate system. They are geometric quantities that represent how scalar fields vary with position. Covariant components naturally describe things like potential fields or surface integrals or the covariant derivative. Covariant vectors, together with contravariant vectors, form important tools in tensor analysis. Interaction with the metric. Covariant tensors are used in contexts where the tensors interact with the metric tensor. For example, in relativity, the covariant components of vectors are often contracted with the metric. That is to measure distances or scalar products. Like when we're calculating the length of a vector, here given in tensor form. So interaction with the metric under contraction and inner product allows us to find things like length. Covariant versus contravariant. What is the role of the metric between the two? The metric tensor, G mu nu, is central to understanding why you might choose one form over the other. The metric defines the inner product and how lengths and angles are measured in a given space. So with that, it also allows you to raise and lower indices, transforming between contra and covariant tensor forms. And for example, if I want to raise the index or lower the index, we use the metric or its inverse to do so. So again, why would we choose one over the other? Well, it depends on the physical situation that you're trying to represent, and also it depends on the mathematical convenience. Convenience in calculations would be of the form, well, sometimes You might find it more convenient to work with, say, covariant components, gradients or one-forms, because they naturally interact with the metric. However, in other cases, contravariant components, velocity, displacement, etc., might be more intuitive for representing directions and motions, i.e., as in describing geodesic paths. Geometrically, covariant components often describe quantities that interact with the geometry of the space, like gradients or differential forms, while contravariant components are typically used to describe quantities that can be interpreted as things like displacement, forces, or moments, things that have directions. So, in summary, contravariant with upper indices. They go along with quantities that involve directions, displacement, velocities, and forces. Vector-like quantities that follow coordinate transformation rules. Covariant tensors with lower indices are gradients or differential forms, measuring tools. They naturally transform in the opposite way to the coordinate basis vectors. And in general, the metric tensor connects covariant and contravariant components, and it plays a key role in determining how tensors are used in different contexts: relativity, fluid dynamics, etc. So ultimately, like in life, the decision depends on the nature of the thing that you are trying to express. Covariant differentiation. Covariant differentiation. Let S be a scalar field. The ordinary partial derivative of S with respect to coordinate x nu is a covariant vector. Thus, the covariant derivative of a scalar is a covariant vector. Now we let A mu be some covariant vector, a covariant vector field of rank 1. The key question we'll ask here is, will I get a tensor by differentiating this vector? How would its derivative change under a coordinate transformation? So if we denote its derivative as A mu comma nu, and its transformation rule is given here with our Bard system, we can write our derivative in the Bard system as follows and use the product rule to expand out this derivative. One notices in doing this that we obtain a second order term, the presence of this term meaning that A mu comma nu is a non-tensor. That is, it does not transform as a tensor properly under the quotient theorem. Thus, the second term must vanish in order for this to give us a tensor from another tensor. So we can modify our differentiation process so to obtain our goal of getting a tensor by differentiating another tensor. We start with the vector a mu, a covariant vector, at some point x, and of course we parallel displace this point to the point x plus dx. Since it is still a vector, we can subtract it from the original vector, and their difference will also be a vector. So to first order our parallel displaced vector at x plus dx subtracted from its original vector, we have this term dA nu, which we developed in our last video under a representation with the Christoffel symbol of the second kind here. And this term right here is a tensor by the quotient rule for an arbitrary dx nu. So we define a nu notation with the colon notation as the covariant derivative of a covariant vector. Now this is our new derivative here, and so we will do a little calculus with our new derivative. And in a natural way, just like you would in a calculus class, we begin to look at the covariant derivative of a product. Exploring the product rule. The product rule is the derivative of a product. And if we ask what is the covariant derivative of a product of two tensors, we have to be more specific. You see, there's an outer product of two tensors. Written this way will increase the rank of the tensor. And an inner product, which is a scalar product, which will result in a scalar. Noticing the upper and lower indices summing over. So we'll begin with the outer product notation, a mu b nu, and we'll take the covariant derivative with respect to sigma. Expanding out using the product rule, we will do some replacement here of our covariant derivative with the Christoffel symbols in place. Noticing here that alpha is our dummy index or our summing index, and sigma is our differentiation direction index. Now we will expand this expression out. Carefully distributing terms, we will then regroup some of these terms together and simplify them. So first thing is we will write this, we'll collect these pieces here together, and we'll collect these pieces here together with the Christoffel symbols. And if we were to let our outer product be given by this second rank tensor, its covariant derivative would follow as through just like this. And thus we can use this model here to finish off our covariant derivative. So what we do from here is we are going to apply this, and we're going to apply this to the metric tensor, because a metric tensor is of the same form as the tensor above. And in the earlier video we proved this relation. So now, what does an inner product look like? Now that we've defined what it looks like to take the covariant derivative of an outer product. We'll recall that for any scalar, the covariant derivative is simply the ordinary derivative. And we can use this to our advantage to define something else new here by expanding out the covariant derivative which is equal to the ordinary derivative. So again, using the product rule, we expand out the covariant derivative, and we can replace this term right here with the notation for the covariant derivative of a covariant vector. And again, because of the fact that this inner product is a scalar, we may also expand it out in terms of its ordinary derivative on the left-hand side. And thus on the right-hand side, we can rewrite this in terms of the covariant derivative of a contravariant vector plus some extra terms. Some of these terms will actually wind up canceling. And because we are free to swap out dummy indices alpha and mu, this can be written as follows. And since this must be true for any arbitrary b mu, we get the covariant derivative formula for a contravariant vector, which appears to only differ in a sign change on the Christoffel symbol term. The laws of physics must be valid in all coordinate systems. That is, in all reference frames. They must therefore be expressible as tensor equations. Whenever physics equations involve the derivative of field quantities, it must be a covariant derivative. You see, ordinary derivatives must be replaced by covariant derivatives in order to make it valid in all coordinate systems. A quick example from physics is the D'Alembertian operator. And if you're not familiar with it, it has something to do with the wave equation, given by a little box with a square for some potential v, which is a scalar. And the operator is given by a spatial second derivative operator minus a temporal term. And if we reformulate this in the language of tensors, we would write this as follows using a second covariant derivative. And since v is a scalar, this expression here, giving 0, shows that a second derivative of a scalar is 0. So this brings up a natural question. What is the second derivative, the second covariant derivative of a vector? And since second derivatives have to do with acceleration, which in turn have to do with curvature, this is going to lead us to something called a curvature tensor. So if we consider a scalar field S and try to calculate its second covariant derivative, we get this expression because scalar fields' covariant derivatives are the same as their ordinary derivatives. And due to the symmetry, we can also rewrite this with the indices swapped. So if we now take a vector a nu and apply two covariant differentiations on it, using the formula for t nu rho from earlier, we can then expand this out in the following way. Now, this is a little bit of a bookkeeping or tedious process to keep your derivatives as you go through and differentiate each part. But careful collecting of terms and indices we get this expression. And what to do with this expression? Well, if we write it out this way, expanding everything and we have all these different terms involving different partial derivatives and Christoffel symbols. So what we'll do is we'll regroup all the terms after expanding them out in this way, where this last term here we can factor out a covariant A beta. The process from here then happens when we interchange the order of the differentiation variable indices rho and sigma. You see, in covariant differentiation, the order of differentiation can matter. So by switching the order and then subtracting the results of these two differentiations, our result is something that we can extract called the curvature tensor. So this quantity here, written out in terms of all of the Christoffel symbol terms of the second kind, the first two being derivatives of those Christoffel symbols, is called the Riemann-Christoffel curvature tensor. And it is based on the second covariant derivative. And it also obeys the quotient theorem. Next, we will discuss some of the properties of this curvature tensor. This curvature tensor has many symmetry properties and parity properties. Thus, if you exchange the third and fourth indice, you are just going to retain a negative sign of the curvature tensor. And if you cyclically permute the three indices below and add the results together, they will equal 0. So now we have two relations for the curvature tensor. If now we use the metric to lower the upper index beta, we get the Riemann curvature tensor with all lower indices. And this action also produces the following result. Here we can represent the expression in terms of Christoffel symbols and the metric. And the symbol on the end there? Well, that just means the preceding terms added to it with rho and sigma swapped. So we may also write this expression solely in terms of derivatives of the metric tensor, plus some terms in terms of Christoffel symbols of both the first and second kind. Further investigation on these expressions shows us that there is also a 1-2 parity law. Swapping the first two indices retains a negative sign. As well as if we swap or flip the first two indices with the third and fourth two indices, we retain the same value. So with all of these symmetries, we can actually take the many components of this curvature tensor and deduce them down to some more important terms. So, conditions for flat space. If space is flat, we may choose a coordinate system that is rectilinear, and then the g, mu, nus are constant. This would then make our curvature tensor vanish because there's no curvature. Conversely, if our curvature tensor vanishes, then one can prove that the space is flat. So the following is such a proof. Suppose the vector a mu, which is parallel transported from a point x to every point in space. Then we have produced a vector field which satisfies this covariant derivative equation, which in other words states this expression. One then asks if such a vector field could be the gradient of some scalar field. And if we let our vector a mu be the derivative, the gradient of some scalar field, represented with its Christoffel symbol here, then we take 4 independent scalars to be the coordinate system of some new coordinate system called the barred system. Then we have this relation. And recall the transformation rule for our metric. Differentiating our metric with respect to x nu, and then subtracting the results, we get this expression. Rewriting things in terms of our Christoffel symbols, simplifying our results here. We get the following result. Thus this quantity equals 0, thus this metric, the derivative of this metric, is 0, i.e. space is flat. The metric is constant. When you're dealing with the second covariant derivative of a tensor, consider an outer product in which we take the second covariant derivative. We would expand it out in this way, carefully using the product rule. Then, as before, we would swap out the differentiation indices and rewrite the expression out, thus then taking the two expressions and subtracting them from each other so that we can extract the curvature tensor. Now, using the form of a second rank covariant tensor, we can express this difference in this way. And thus, if we allow that to be the covariant derivative of a mu tau, we can then simplify this expression for the general second covariant derivative. Then what we can do is we can take cyclic permutations of tau, rho, and sigma and add the resulting equations together. This is a lot of index homework here, but sticking through with it, you get the right-hand side to reveal this, plus the cyclic permutations with all other terms vanishing. And thus we get this equation to hold true. And canceling out all the factors of A alpha in this expression, we get an expression in terms of just the derivatives of the Riemann curvature tensor. Thus, the Riemann curvature tensor satisfies these differential equations. And together with the symmetric properties we discussed a little earlier, we call these the Bianchi relations. Well, that's it for this video. I hope you really liked it. Please stay tuned for the next one, Chapter 4, and hit that like, subscribe, and notification bell for more videos. Thanks for watching and stay tuned.